Acids and bases. Some examples of acids are hydrochloric acid or muriatic acid, nitric acid, phosphoric acid, and sulfuric acid. Can you find out something that is common among these acids? Bases examples. Some common bases examples are alka-cercet, drano, eggs, watermelon, baking soda, and Tums. But how can I tell the difference between them? With this chart, probably we can begin knowing how to get the difference between them. First, acids, they taste sour, whereas bases, they taste bitter. Acids, they exhibit a pH between 0 and 7, whereas bases, they exhibit a pH of from 7 to 14. Acids, they are corrosive to metals. Bases, on the other hand, if you touch them, they feel slippery. Acids, usually, you will find them with a hydrogen ion because they are proton donors. Bases, on the other side, they are proton receivers, and most of the time you can find a hydroxide ion between them. So this is to sum up: sour, bitter, itchy and burning feeling at the skin, slippery. They're donors of hydrogen ions, whereas the bases, they're receivers or acceptors of hydrogen ions. Now, there are different theories about acids and bases, but three are the main ones. Let's begin with the first one. And the first one is Arrhenius. Arrhenius found out that acids form electrolytes that include the hydrogen ion, H positive. Bases are substances that produce the hydroxide ion, OH. Nowadays, we know that acids solutions do not contain simple hydrogen ions, but hydrated protons, H3O+, also known as hydronium ions. According to Arrhenius, there are three kinds of acids: monoprotic acid, diprotic acid, and triprotic acid. Monoprotic acid. There are acids that are able to donate one proton per molecule during the process of dissociation, sometimes also called ionization. As we can see here, a monoprotic acid dissolved in water can yield to hydronium ion plus the anion, both in aqueous solutions. A diprotic acid, here symbolized by H2A, can undergo one or two dissociations depending on the pH. Each dissociation has its own dissociation constant, Ka1 and Ka2. We can see that in the next reaction, when we have a diprotic acid dissolved in water that yields to hydronium ion plus the monoprotic acid. After that, the monoprotic acid dissolved in water turns back again into hydronium ion and the anion. A triprotic acid can undergo 1, 2, or 3 dissociations and has 3 dissociation constants, where the first dissociation constant is bigger than the second and bigger than the third. In here we can see that the triprotic acid is turned to a diprotic acid. The second, we have a diprotic acid turned to a monoprotic acid, and in the last reaction the monoprotic acid is decomposed into a hydronium ion and the anion, each one of them with their constants of dissociation. Now is your turn. Identify the next acid as monoprotic acid, diprotic acid, or triprotic acid. Stop the video, do them, and when you are done, play it back so you can compare your answers. Good luck. Acids and bases theories, Bronsted and Lowry. According to Bronsted and Lowry, we have an acid that is a giver of a proton, whereas a base there is a receiver. A Bronsted-Lowry acid is defined as any substance that can donate a hydrogen ion, which is a proton. And a Bronsted-Lowry base is any substance that can accept a hydrogen ion, that's a proton. Donor, receptor. Thus, according to Bronsted-Lowry definitions, acids and bases must come in what is called conjugate acid-base pairs. For example, consider acetic acid dissolved in water. Which one do you think is the donor and the receptor, acetic acid or water? And the winner is acetic acid is the donor, whereas water is the receptor. So, acetic acid will be the acid, whereas water will be the base. In the product side, you can see hydronium and acetate. Which one do you think will be the donor, and which one will be the receptor? Yes, the donor will be hydronium and acetate the receptor. So, hydronium will be the conjugate acid and acetate the conjugate base. Based on this information, it's your turn to try this. Identify the conjugate acid and bases in the reactants and product side. This is the reaction. Now, stop the video, decide who is the acid, who is the base, who is the conjugate acid, and who is the conjugated base. When you're done, play the video back again so you can check your answers. Good luck. According to Bronsted-Lowry, we can also have what is called amphoteric substances. You may possibly have noticed, although probably not, that in one of the last two examples, water was acting as a base, whereas in the other one, it was acting as an acid. A substance which can act as either an acid or a base is described as being amphoteric. In this example, we can see that water can get a proton, converting it to hydronium and becoming a base, whereas water can give out one hydrogen, and so it becomes an acid. Acids and bases theories. Lewis. A Lewis acid is a substance that can form a covalent bond by accepting an electron pair from another substance. A Lewis base is a substance that can form a covalent bond by donating an electron pair to another substance. So in here we are talking about the electrons, and one is the acceptor, that is the Lewis acid, and the other one is the donor, that is the Lewis base. In the example that we have at the bottom, we have a hydrogen and we have an ammonia. Ammonia is the donor or giver of electrons to hydrogen to form ammonium. In this case, as it is the giver, ammonia will be the Lewis base and hydrogen will be the Lewis acid. In the example number 2, we have ammonia with boron trifluoride. In here, as we can see, ammonia is the giver of the electrons and boron trifluoride is the receiver of those electrons. So as ammonia is the giver, so it becomes the Lewis base, whereas boron trifluoride is the Lewis acid. To sum up, Arrhenius acids were the ones that had hydrogen ions in an aqueous solutions and bases hydroxide ions in aqueous solutions. Bronsted-Lowry acids were givers or acceptors were givers of protons, whereas the bases were acceptors or receptors of these protons. And finally, Lewis acids were the ones that receive electron pairs, whereas the bases were givers or donors of these electron pairs.